also I would like to thanks for everyone to come and listen to a very nice lecture. Okay, so which is about algorithms and robots for chemical discovery. So our speaker for today is from Kazakhstan. Okay, but he did his bachelor's at the Korea Advanced Institute of Science and Technology in 2022. Then he is now taking his PhD studies at UNIS, or the Ulsan National Institute of Science and Technology in Korea also. So he will be talking about his new paper, which was recently published in Nature, about robot-assisted mapping of chemical reaction hyperspaces and networks. He is actually a student of Grzybowski, if you know him. He's a very famous one with regards to AI and robotics in chemical science. He actually in Harvard, I think, right? Yeah, Harvard University. Okay, Galjan.
Thank you, Professor Balaman, for such a warm welcome here and nice introduction. So my name is Galjan Moldagulov. Thanks to every one of you for coming here today to listen to my talk. I'll be giving you a brief introduction about our research center, the Center for Algorithmic and Robotized Synthesis, which is actually a part of Institute for Basic Science. It's a Korean analog of Max Planck Institute in Germany. So yeah, a brief introduction of myself. I was raised in the city of Achtau in Mangostal region. You can see the beautiful view from the Caspian seashore of our city. And after finishing high school, I decided to pursue chemistry, and specifically I applied to South Korean universities. So one of my top choices for my bachelor's was Korea Advanced Institute of Science and Technology, where I successfully defended my undergraduate thesis on photochemical degradation of polyethylene glycol. And afterwards, after my bachelor studies, I decided to go to graduate school. For some time, I've been a PhD student in Pennsylvania, the Pennsylvania State University, and there I was also teaching a organic chemistry laboratory course. But just doing organic synthesis was not enough for me. I also wanted to include machine learning and other artificial intelligence algorithms for my research. That was the point when I decided to apply to Ulsan National Institute of Science and Technology, where I am right now working together with my research advisor, Professor Bartosz Grzybowski. He's actually a Polish researcher who was doing his graduate school in Harvard together with Professor George Whitesides, and he was mainly focused on nanotechnology. But after some time, he decided to work on chemoinformatics and specifically reaction informatics. And today's talk is going to be a brief introduction of that field first, and then our recent discoveries. So when we talk about organic chemistry, when we plan our experiments, usually the picture looks something like this. So it's a lot of different flasks that are interconnected between each other with very complicated schemes, or maybe not so complicated. And the main goal of organic synthesis is getting valuable functional materials. These materials can be used as potential drugs or as different photoelectronic devices. For example, most of the smartphones nowadays of Samsung, they use organic electro materials. So the organic chemistry in practice looks like this, but when we describe it on paper, it's usually quite neat schemes, the reaction schemes, when our reactants A and B combine together under certain conditions to give a product C. But there is a slight problem with this notation of organic reactions. Actually, when we are executing our synthesis, there are a lot of different parameters, a lot of different intermediates and byproducts that we have to take into account. And all of these reactions, they come together to make a network of organic transformations. All of these networks, they can be described as a set of organic reactions. And let me introduce the mathematical networks that make the foundation of organic chemistry. On this slide, you can see the cover of Angewandte Chemie journal in 2005. It was a time when Professor Grzybowski, with his first students, they decided to describe the entire organic chemistry space in a single picture. So this whole interconnected graph represents all of the typical organic substrates and products, and all of them are connected through edges that represent chemical reactions. So this ability to navigate in such a tightly interconnected network is the most valuable skill that organic chemists have. And when we talk about navigating this big space of different reactions, we can also talk about computers and how they help us doing it. The very first examples of using computers and algorithms for organic chemistry, and specifically for planning the synthesis, was the very first example of such software, the abbreviation LOHASA, which stands for Logic and Heuristics Applied to Synthetic Analysis. And the creators of this program were the team of renowned Harvard Professor Elias James Corey. So they used the very first examples of computers, which were very bulky, and they were able to execute quite simple calculations. And they devised a whole methodology to plan out the synthesis of a target molecule. So here you can see the retrosynthetic tree with all of the different pathways that you can take in order to synthesize our target material. The main feature of this retrosynthetic tree is ability to filter out inefficient synthetic routes and focus on only the relevant ones or the ones with the lowest cost. Even though their discovery in the late 60s and early 70s, it was quite groundbreaking, using such software was still not that efficient. This is because of the limitations in computational power. So you had to navigate this retrosynthetic tree manually, and all of the decisions were made by human users. So fast forward through the years, there were numerous different retrosynthetic software published, and until 2000s, most of them, they didn't really see applications in industry. But afterwards, coming with the groundbreaking software for retrosynthetic planning, the Chematica, later renamed as Cynthia by our research group, paved the new motivation to study retrosynthetic analysis using computers. So as you can see, post-2000s, a lot of pharmaceutical companies, they started investing in such projects, and they made their own versions of Chematica, such as the IBM, the MIT guys with their ASCOs, the SciFinder, and Reaxys retrosynthesis. So let's look at a typical workflow for such retrosynthetic programs. We select our target structure. It can be either a drug or a complicated natural product. And we would like to get the output as the best synthetic route of all of the possible reaction routes. So Chematica, which was the product of Professor Grzybowski's lab, was able to provide not only the most efficient ones in theory, but useful in practice. And Chematica was based on a whole data set of organic reactions encoded in a machine-readable way. And the total data set up to the point of 2017 has counted more than 110,000 different organic reaction types. Not just the examples with different substrates, but distinct reactions with their distinct mechanisms. A typical organic reaction rule that was encoded into a machine looked something like this. Here we can see the example of Manning reaction, the main transformation with only the reactive sites of our substrates and the products. And this chemical transformation can be encoded in the form of a text. This reaction rule is also supplemented with very practical information, such as the functional groups that we have to protect in order to execute this reaction, and some of the incompatible functional groups. And also a typical set of reagents that we need to use. Finally, we can backtrack all of these reaction rules from their source publications and see whether the reaction rules, they were indeed properly encoded into machine. If you have never heard about Chematica, here is a perfect example that it was always there for us. Actually, Chematica and its commercial name Cynthia right now can be accessed as a plugin of the Chemdraw software. I guess most of the researchers working on organic synthesis, they already use Chemdraw. So using the retrosynthesis planning for their own purposes also can be achieved using Cynthia Chematica. So let's start our example of retrosynthetic analysis. For this purpose, we selected the same molecule that I just presented to you a few slides before, and we start our analysis. Here is the sensible molecule, the exact identical copy of it, and radially we can see a tree, the graph extending towards all of the possible precursors that can lead to this target structure. But a very good question arises. All of these precursors, yeah, they can lead to this target structure in one single reaction, but we still have to synthesize them somehow. So some of these precursors are quite complicated in their structure, and the answer how we can access them is iteratively executing the retrosynthetic analysis. So now, if we select this exact precursor, we can access it via combination of this alkyne and also the triazide. And we can continue this iterative process until we get a lot of different possibilities how we can synthesize a purple molecule. And sometimes the number of such diverse reaction routes can increase to astronomical amounts and lead to a picture like this. So here we can see more than 100 different strategic reaction routes. Yes, so we can actually plan all of this and get a reasonable chain of reactions, chain of transformations to access our target structure. It works well in theory, but do we actually see applications in the synthesis itself? And in 2020, our colleagues from our lab, they actually proved that all of these best synthetic routes predicted by Chematica Cynthia can be actually applied, and with quite good yields. So in this paper, they analyzed 7 different natural products, and here is one of the examples, the natural product alkaloid tacomamidine. And the output, the best synthetic route of Chematica, is presented as a graph here, and also as the sequence of reactions executed in the lab, along with all of the yields and the diacetyl selectivity of our product and the enantiomer selectivity. And as we can see, most of these yields, their range fall beyond 50%, which is actually quite a good yield for organic reactions. And some of the reactions, they also cover like 90% of the transformation. If you are not convinced that our own proof of concept is not enough, if you think that it's not enough to convince you to use this program, there was also a separate independent study conducted by Professor Tim Cerner in the University of Michigan, and they tried to analyze how well Chematica can predict the routes and how good they predict in comparison to humans, to organic chemistry experts. In order to do this, they selected the natural alkaloid, this stemoamide, shown here. And for this product, there were already known 32 different total syntheses. And the shortest one of them was executed in 7 synthetic steps. Chematica was able to conduct the retrosynthetic analysis, and most of its successful synthetic routes, the top 10 of them, they were all based on the strategic reaction, the mannitide disconnection, which is shown as the reaction number 3 here. And this strategy allowed synthesis of stemoamide in only 3 synthetic steps. So when you're talking about organic synthesis, where you're constantly losing some proportion of your starting materials due to yield limitations, getting your final product in the shortest amount of steps is very crucial for us. And here, I just wanted to raise a question for the audience. How do you think? How much time would it take for a very expert organic chemist to design a whole plan for synthesizing this giant monster here? And by the way, one more question. How do you think, what's the name of this compound? So I'll give you a hint. This compound is very popular nowadays. It's a drug that Americans and Europeans use a lot. Any ideas?
Weight loss.
For weight loss?
Yes.
Yeah, exactly. This is the so this is the drug Ozempic, and our software, the Cynthia, was able to plan out the whole synthesis for Ozempic and give the best possible route in just 11 minutes. But for human experts, probably it would take much more time than 11 minutes, counting in weeks or maybe sometimes in months. All right, all of these mathematical networks that can be applied for organic synthesis, they all are based on already known reactions, known transformations. But how about making new discoveries? So one question that I wanted to address today, can we discover such networks algorithmically and make new chemical reactions? In order to answer this question, let's get back to our encoded reactions. And instead of just writing down the whole transformation, what if we could encode the entire mechanism of a reaction? So all of the sequential steps along with their byproducts. And this is exactly what our research team did after successfully selling Chematica Cynthia to Merck in 2017. They decided to now address the inverse question. If you have a predefined set of substrates, what possible chemical compounds you can actually create with this? And they decided to found another software, which is right now is called Alchemy. Thanks to the success of the previous software, now these two companies, including Bruker, that we all know, the manufacturer of NMR spectrometers, they decided to fund this project. And the main advantage of Alchemy over other alternative is that this software has encoded the mechanistic steps of organic reactions. So one of the use cases of Alchemy is shown here. This is a network of prebiotic chemistry. we can see the input for our software, a combination, a collection of inorganic compounds, quite simple ones, such as methane, ammonium, water, HCN, the nitrogen, and hydrosulfuric acid. And from this combination of different compounds, we can achieve quite a lot of new structures. So all of these 6 compounds, they are represented on the lowest row, noticed as generation 0. And all of the next rows, they can be created from a combination of rows below. So all of the rows from G2, they are the products of different combinations of G1 and G0. And apparently, if we let our software do the forward synthesis prediction, it encounters biotic compounds, so the biomolecules such as the lemon acid and also different nucleic bases. If we remove all of the noise from this reaction network and we just focus on biomolecules, the alchemy have encountered quite a lot of different amino acids and sugars and also peptides. And we can trace down their formation, the sequence of organic reactions that leads to these compounds just by looking and analyzing our network. So here is the example of adenine and how it can be created and all of the possible routes leading to adenine. And what is more impressive is the fact that most of these transformations, they were already recorded in Urey-Miller type of experiments when organic chemists, they mixed different abiotic compounds and tried to analyze this prebiotic soup. Okay, maybe analysis of prebiotic mixtures is a very philosophical question, the origin of life. And most of organic chemists, they would like to see something that they can use in practice, something that can bring the difference in manufacturing new compounds. So here is another example case of alchemy for discovering novel multi-component reactions. Our alchemy in the new 2 publications that were published in Nature Communications last year. In this project, our colleagues gathered a whole collection of different commercially available precursors. To be exact, more than 2,400 different compounds, and encoded nearly 8,000 different mechanistic steps from organic reactions. And they let alchemy do its thing. Upon analyzing the chemical network that arises from this forward synthesis prediction, we also build up the complexity of our analysis in 3 steps. So we can see the formation of main compounds, the main products of our mechanistic steps, and also track down the byproducts of the 2nd degree of importance. And similarly, all of the products that can be obtained from the byproducts of the 2nd degree importance. So let's give it a try. Let's give it a try for alchemy and predict what can be made from this combination of 3 compounds. Let's try to cook the new multi-component reaction. So on the first level of our analysis, we can see that only a single novel compound that was not ever described in any of the chemical database was found. And if we take into account all of the different byproducts and their different transformations, now the picture is more diverse. So we can see more of the compounds that were not described in databases. And all of these mechanistic transformations within the network, they can be traced down to the literature precedents and see how chemically plausible they are. And here on this slide, I would like to present to you the very first example of multi-component reaction discovered entirely by an algorithm without any intervention from organic chemists. So this is the multi-component reaction leading to this kind of framework. And the substrates go for this reaction. And as you can see, our colleagues in our laboratory, they also proved that these reactions take place in flasks. So with quite high yields, up to 90%, 60%, and etc. And this is not it. When running the forward synthesis task, we're using alchemy on different collection of substrates. We were able to discover even more different multi-component reactions that were later proved to be effective in the lab, and more. And most of these novel products that can be made from these multi-component reactions, they are heterocyclic compounds that can be potentially used as different functional materials for absorbing light or for electromagnetic properties and etc. So the answer for the question, can we discover such chemical networks using algorithms, is absolutely yes. But a very good question arises when we cook organic reactions in the lab. Why don't we see the picture like this within our flask? Why we don't see all of these reaction networks and different transformations with our own eyes? Our guess, our research lab's guess, the reason for this might be the way how we learn organic chemistry. So most of us learn typical main reactions as a sequence of mechanistic steps. So there is a predefined mechanism, and all of the transformations are done sequentially. But in reality, all of the organic reactions, they should be described as networks, not just a linear sequence of transformations. So we decided to explore more and ask ourselves the question, can we control these reaction networks using experiments and see them in practice? To be more exact, these reaction networks can be described as kinetic networks. So all of the transformations between intermediates and different byproducts, they can be further described using kinetic constants and also the activation barriers for every single mechanistic step. Some of these transformations are going to be faster and more dominant, leading to the majority of the product, and some of them are way slower, and these pathways, they lead to a minor product. And on top of that, based on the initial conditions of our reaction, we can also encounter different outcomes. So here we have the plot with the concentration of our reactant A, the concentration of reactant B, and the very simple reaction network with two different products. So as you can see, if we select our initial conditions in the blue region with excess of product of the substrate B, then the product B2 is dominating. And if we select our initial conditions from the red space, then instead our other product is dominating. So in order to study these kinetic networks of organic chemistry, we have to execute quite a lot of experiments. So with the number of parameters that you would like to change and sample, the number of experiments also increases exponentially. So with one parameter that you would like to change the condition and measure its outcome, let's say as a yield of a reaction, you can execute only 30 different conditions and get quite nice distribution. If you would like to change 2 different parameters, then the number of reactions you have to execute is counted with hundreds. 3 different parameters, now we're talking about thousands of reactions. And let's see what is the state of the art in studying such reaction networks. Selective methylation, we have 2 different parameters to change, and only 50 experiments for this reaction. Another published article of selective methylation, now 3 different parameters, and we can see that the amount of experiments done doesn't really represent our entire hyperspace of initial conditions. So there is some picture forming of our initial condition hyperspace, but it's not sampled densely. Another example was more than 1,000 experiments. There is already a nice distribution across 2 different parameters, but only a single maximum of yield. The most crucial organic transformation for medicinal chemistry is coupling. More than 1,000 experiments done in 2 different studies, 2 different parameters that were analyzed. And in this case, they sampled only the conditions for optimizing the yields, so they didn't really do an exhaustive sampling. And the largest experiment that was ever done for studying reaction networks was more than 6,000 of different experiments for Suzuki coupling and also for Buchwald-Hartwig amination reaction. But the problem with the study is that they only measured the mass spectrum of the products formed. So they didn't really get the quantities of products, in what yields they were formed. So based on this, we can make a few conclusions. Our knowledge of such condition spaces, hyperspaces, is very limited, and most of the different campaigns for screening different conditions, they are done only for optimizing the yield of a reaction. Or let's say, alternatively, is optimizing an anti-selectivity. But our goals in our laboratory is completely different. We would like to study mechanisms of reactions and see the reaction networks for our organic transformations. And in order to do this, we have to measure the yields, the outcomes of our reactions as well. So we decided to use a very simple characterization technique, the spectrophotometry, and literally take a photo of our reaction mixture. If we change 3 different parameters, so let's say the concentration of our substrate A, substrate B, and also the temperature, we can get roughly 100 different conditions and the reaction mixtures. If we combine all of them together into a big soup and try to isolate all of the components using high-performance liquid chromatography and measure the spectra of every single component separately, we can get calibration curves. So these calibration curves are the UV-vis spectra of all of the isolated components at different concentrations. And using this basis set of spectra, now we can analyze every single point within our condition space. If we take a UV-vis spectrum for this particular point, we probably will see a picture like this. So there are distinct absorption bands, but we can't really say in how much concentration you get A, B, and C. But using basis sets, we can actually do a spectral decomposition and actually quantify every single component. And this can be done thanks to the Lambert-Beer law that we study in analytical chemistry. So using our calibration curves of different concentrations, we can do a linear regression and get an answer in what quantities every single component is present in our reaction mixture. So to do that, only the visible spectrum might not be enough. So here is the example for one of the reactions we studied in our project, the Hunch reaction. 16 different components. So you can't really say much from this window of our spectrum. But if we include the ultraviolet range, then we're talking. So we can see different absorption bands and decompose our spectra. To do so, our colleagues, they devised a machine learning algorithm for that. And this machine learning algorithm also takes into account the stoichiometry of our mechanistic steps. So taking into account the stoichiometries, we get the system of inequalities to take into account the mass conservation. And finally, the machine learning algorithm was trained on this cost function, which is based on two parts. So the first part is the mismatch of the actual spectrum and the reconstructed spectrum. And the second part is the violation of these stoichiometric inequalities. So by optimizing over this function and minimizing its result, so closer to zero, we can reconstruct spectra. So a successful spectral decomposition would look something like this, as presented on the left side. So the difference between our experiment and the model should be within the instrumental noise. So as you can see, the difference in spectra fluctuates without any correlation within like 0.01 of the absorbance. But if we didn't have enough components to fit our spectra, then the inadequate model would result in the spectral difference, which has correlations with quite a big amount. So with this methodology in hand, we decided to use it and name it our method OES, so Optical Yield Estimation Scheme. And the main point of the scheme is to reconstruct the spectra of individual points using our calibration curves. And now here comes our DIY laboratory-made robot that we called Robowski in honor of our research advisor, Professor Zhibowski. And this robot allowed us to sample our condition space with an extraordinary throughput of almost 1,000 reactions with yields per single day. The robot has several different components, and the entire scheme costed less than $25,000 for us. This is quite impressive for a university lab because commercial alternatives for such high throughput experimentation systems, they usually cost more than $100,000. So the entire scheme of our robot, all of the blueprints and the software used to control it was published in open access on platforms GitHub and Zenodo. So if you ever decide to build your own copy of Robowski and use it for your experiments, you can build one using our information. So yeah, in this robot we got the main components. So these are the XY gantry that control the displacement of our electronic pipette in XY plane, then the electronic pipette that actually mixes our compounds together, and the custom edited spectrophotometer, which is actually used for water-based mixtures, but we tweaked it a little bit to handle organic solvents as well. The entire reaction mixture preparation process and spectrum acquisition is fully automated and can be controlled through our script, Python-based script. And all of the corresponding spectra can be acquired in real time. There is a distinct scope of our OES method. It can be applied for different condensation reactions, and also for typical catalytic transformations like Suzuki coupling, Buchholz-Hartwig amination, and also Sonogashiri coupling. But if you decide to use our method with very absorptive components that can block the entire UVB spectra, then unfortunately this method can't really estimate yields properly. If you also encounter a lot of precipitate, then probably we need to address a different characterization method. Finally, if your reaction components are all aliphatic and they don't absorb UVB's range, then also another alternative should be used instead. Luckily, for the reaction scope, when we measure our yields using optical method, all of the quantities, they well correlate with typical quantization of yields using NMR standards. There's a quite nice linear fit and reproducibility. So now let's finally talk about chemistry, about different reactions that we'd like to study. Here's the very simple example, the very first type of reactions that we ever study in organic chemistry, the E1 elimination reaction. Here are our substrate, product, and also a brief mechanism. So using our Robovsky, we sampled nearly 800 different reaction conditions. And after interpolating our raw data, we were able to see clearly the distribution of our yields. So here we can see a very distinct region in space with very high yields. And then the isosurfaces, they represent yields in 80%, 60%, and so on. So using this data, we were able to extract thermodynamical parameters for our reaction, get kinetic curves, and calculate the enthalpy and entropy of our reaction. Another example, the nucleophilic substitution of the first order, the SN1 reaction, using the same optical yield estimation in our Robovsky, we got a lot of points, calculated our thermodynamical parameters. So now everyone can say, yeah, you guys can do your experiments very quickly with unprecedented speed. But does it really allow you to discover something new? Is it just the matter of making experiments fast? And we have an answer for this. So here we studied another quite boring example of reactions, another example of SN1 mechanism, but we encountered an anomaly. So in this reaction, we got our main product, and the distribution of yields is shown here in this hypercube, and the already known, already published side product, which is a result of a oxidation of our initial substrate. And the distribution for the side product is shown here. But in this hyperspace of our initial conditions, there is a very narrow region of space which doesn't really fit into our UVB spectrum. So we decided to investigate and find what might be the component that has a very distinct pinkish tint within our reaction mixture. So we went to already known publications and tried to see whether some of the hypothetical structures that can lead to this absorption spectra, if they correlate with our experimental results. And most of the carbocations that we investigated, they don't really fit to the spectrum of our reaction group. So we decided to go further and do our own simulations using quantum mechanics and show a basis set and functional. And we tried to see whether this pink compound, the unknown compound, can be a radical. But the simulated spectrum didn't really fit. maybe it can be a radical cation, and it didn't fit as well. Can it be a dimer structure, the dimer of our initial substrate? And finally, we saw that the UVV spectrum did correlate with our experimental findings. Upon further investigation, we got the mass spectrum of our reaction mixture, and we indeed saw distinct peaks that has exactly the same molecular mass of this dimer cation. We think that this structure might be a result of dimerization of the cation of our substrate. And finally, we saw the real reaction network for supposedly boring SN1 type of reaction. Yeah. If we read further in our paper, then you can see that this type of dimeric cations, they usually form under very high temperatures. But in our experiments, we used only the range from room temperature until 40 Celsius degrees. So now we saw how we can use it for anomalies. And we investigated reactions with a very distinct region with a single maximum. But can there be organic reactions with multiple maxima in the condition space? So to investigate this, we decided to choose the classical multi-component UGI type reaction, which led to this heterocyclic product. And we sampled the 4-dimensional hyperspace of it. So we changed not only the concentrations of our substrates, but also as a 4th dimension, we changed the concentration of our catalyst. And from this animation, you saw that there are 2 distinct maximas for this reaction. It turns out that the global yield maximum proceeds through the main mechanism of UGI type of reaction. But in the local yield maximums region of our hyperspace, there are multiple different side reactions that happen. And they interfere with our main mechanism and compete for substrates. So here you can see highlighted in red compounds, the more or less stable intermediates that we saw in our reaction mixtures, and we were able to quantify the yields of these red compounds. Finally, we were able to reconstruct the entire mechanism for UGI type of the UGI reaction, and saw that indeed these side reactions, they do interfere with our main mechanism. We tried to fit a theoretical kinetic model for this reaction mixture, and saw that our theory does really correlate with our experiments. So as you can see from another perspective, the 4-dimensional animation. Okay. So if we see at the 4-dimensional perspective of our reaction, we do see the global yields and the global maximum and the local maximum of our reaction. So the answer for the question, can we control these reaction networks algorithmically, is absolutely yes. And finally, we wanted to investigate the last question. Can we really switch between main products of our reactions? In order to do this, we selected another classical example of multi-component reaction, the Hansch ester synthesis, which was discovered in the 19th century. And supposedly, how can I really surprise you with a reaction that was already studied for such a long time? It's already known that this reaction can proceed through 2 different reaction modes and lead to a thermodynamic product, which forms under high temperature, and the kinetic product that forms at the shorter reaction times and smaller temperatures. Using our high throughput experimentation system and the optical yield estimation in the closed loop, we decided to reconstruct the network of Hunch reaction. So let's do it step by step, the reconstruction. We select our substrates of the reaction and the main product, the Hunch ester. So using all these 4 components, we try to fit our spectra to UV-Vis measurements, and we see that the error of our spectra, they lie quite high and very distant to the instrumental noise limit. But for proper reconstruction of networks, we would like to see our statistical noise very close to the instrumental limit. So we decided to add more components to our reaction mixture and isolate our byproducts using reverse phase chromatography. And we're able to identify this competing reaction that leads to another pyridine. And on top of that, the side reaction, the oxidation of our main product into aromatic compound. So now using 7 components, our spectral mismatch did decrease. So we are going in the right direction. We go further, we isolate more components, more byproducts, and add them into our fitting. And with the increasing number of components, we do get closer and closer until we finally converge along with the instrumental noise limit. So here is the UV-Vis spectra for all of the 16 compounds of our Hunch reaction, the entire basis set. And using this basis set, we were able to reconstruct the network of our reaction. So here we have the main process, the formation of the Hunch ester, then a competing side reaction, another known multi-component reaction, the Petrenko-Krishenko reaction, and many multiple other side reactions. And we tried to reproduce the results of these transformations in ex roboto experiments. So we actually took the exact same structure of this intermediate and we tried to cook it outside of robot in flasks. And indeed, the experimental results, the yields, they proved that these transformations they take place in the mixture with quite good yields. And finally, we see an example of a switchable reaction that can be switched only based on the proportion of initial substrates. So in our hyperspace of conditions, we can see a distinct corner where the reaction mixture results in the Hunch ester. Different corner and you get the Petrenko-Krishenko product. Another distinct corner of our hyperspace and we get our novel compound that was not previously described for the same system, the Hunch reaction, and we decided to call it using our robot, so the Hunch Robovsky product. And finally, as a cherry on top of our cake of our project, we decided to see whether algorithms that were investigated at the very beginning, do they really correlate with our experimental results? We tried to make the forward synthesis prediction using the same set of substrates and expanded over multiple generations. And we do see that the algorithm predicted exactly the same byproducts and main products as the ones that we discovered using the robot. If we remove all of the noise, and focus only on the compounds taking part in our reaction network, then we see this picture. So the answer for a question, can we switch between major products? in reaction networks is absolutely yes. So some of the conclusions from today's seminar is that algorithms and robots, they're already here. It's 21st century, and a lot of different the synthesis campaigns in particular, they already use the state-of-the-art technology. And in order to become successful scientists, we have to somehow adapt these new algorithms and robots to do our research more efficiently and more faster. These robotic systems, they enable not only executing reactions faster, but also discovering new chemistry. Previously impossible just from the typical experiments where a single person executes a single reaction a day. And finally, is the fact that organic chemistry is not linear. It's not just a sequence of linear transformations, but rather a very tightly interconnected reaction networks. So this project was ordered to be published in the Nature journal this late September. And in this project, a diverse team of 15 experts from 10 countries participate. And all of these experts, they gathered in our Center for Algorithmic and Robotized Synthesis. And I'm very proud to be a part of this multinational and diverse team of physicists, engineers, and organic chemists. So I would like to acknowledge the support, the continuous support from our university, Rusan National Institute of Science and Technology, as well as our research center, Center for Algorithmic and Robotized Synthesis, which is part of Institute for Basic Science. I'd like to say thank you to all of my lab mates, our entire Zhibovsky lab, and also to every one of you who came to listen to this seminar and supported me in this endeavor. So thank you very much.
Thank you very much, Katarina. So it's a very interesting talk, and that is actually a well put system wherein you have the AI and the robots, including chemistry, are all put together in this. So any questions? Questions? Yes, Professor Kaliman.
Well, thank you. It was a very interesting talk indeed. I'm an organometallic chemist, and I'm doing things with coordination compounds that widely used as homogeneous catalyst for a variety of organic transformations. So, and for a while I have a question in my head whether it's going to be as simple to make something that can predict the reactivity of transition metal complexes, as in this case for organic synthesis. Because organic chemistry is using a very definite set of rules and mechanisms, right? So, and when you go to transition metal chemistry, things become significantly more complex, unpredictable, and sometimes even unknown. What do you think? Whether it's possible or not to develop something like that particularly for catalytic applications, to discover new catalytic reactions with transition metal compounds?
So this is a very interesting question. Can we really apply same algorithms or maybe extended versions of it to discover new catalytic reactions where organometallic compounds really control the outcome of the reaction? To answer that question, I would like to remind how since the alchemy software works. So it works on a database of mechanistic transformations. So this whole set of mechanistic transformations would only cover typical organic compounds, elements, so p-block elements. But in order to do the same thing with organometallic chemistry, I think that we need to encode these reaction rules as well, so mechanisms. So let's say the oxidative addition steps within the catalytic cycle might be the transmetallation part, the reductive elimination, and all of the different insertions and translocations within the complex. So yeah, I think that with the similar approach, we have to gather data and then do experiments. But if we would like to automate it, we can use it using machine learning. So instead of supplying this quality data, you can just let machine learning algorithms and try to let it try different arrangement of electrons between all of the atoms. So yeah, I think state-of-the-art forward synthesis prediction, it doesn't really cover elemental chemistry, but we might see good projects published soon, maybe in next 5 years.
Yeah, thank you. Well, because I see that it's a little bit more complicated than a classical organic chemistry. Yes, there are certain, typical reactions, as you said, oxidative addition, reductive elimination, migrations, insertions. But all of these reactions are highly dependent on many different conditions, right? So, I mean, ligand donating properties, steric environment around the metal itself, right? So you might change metal in the same group, everything changes. So, and I'm kind of wondering how difficult would it be to incorporate all these tiny, small nuances in the predicting tool. So, okay, well, thank you.
Thank you very much for your question.
Thank you very much. So it's doable, but again, it's all about the data set that you're actually going to input. Any other questions? Yes.
So thank you, Alan, for your very interesting talk. I had a chance to recall all my organic chemistry knowledge from university, from lectures, because myself I'm a protein design researcher. So I'm more interested in like two sides of your project. The first one is about machine learning. So I'm interested, how do you encode those features, like as you said, in the form of text? But I'm more interested how exactly and which algorithms you used in order to encode those features. And this is the first question. And the second question is about protein science. In your opinion, can we use those robots or anything related to it to synthesize maybe small peptides? Yeah.
Thank you for your wonderful questions. So let me answer the first one. So the first question, what kind of features we input into our machine learning algorithms? So on what information, the structural information, and maybe stereoelectronic information, we can make certain decisions and predict certain parameters. So typically in organic chemistry, we represent all of the molecules as graphs, as mathematical graphs. These graphs, they have nodes for atoms, and all of these nodes, they are connected with edges. So every single such node, it carries its own information. For example, the atomic number, maybe the occupancy of the last shell of electrons, and probably a formal charge for a given structure. The edges, they also carry information about the bond order and etc. So using such information, we can do predictions. What kind of algorithms we use for that? So right now there are a number of good papers published in JAX and also in Nature in Angewandte Chemie, where they use simple linear regression. Some data science specialists or some computer scientists might say that it is like a kindergarten. Why are you guys using just simple linear regression or logistic regression? But I think as long as it does its job and it's used, can be used in practice, we can surely use such algorithms. If you want to go further and solve more complex problems, we can use neural networks, or maybe decision trees, or other algorithms such as XGBoost or maybe even generative neural networks. So coming to the second question. So as you mentioned, as I understood, you're working with proteins, you're designing proteins. How can we use robots to enhance this research field? As far as I know, many pharmaceutical companies, they already use high throughput experimentation, and they try to see whether like different designed antibodies or synthesized antibodies, whether they interact with the chemoreceptors, with antibody receptors. So yeah, the question can be answered yes. Robotics absolutely can help in making progress in this field. Can we discover new peptides? And peptides meaning much smaller structures? Also yes. So as I showed earlier in the slides, with the prebiotic network of organic transformations, we can do the same Urey-Miller experiment, where we combine different combination of starting materials and let them react together for a long time and analyze this complex reaction mixture. As far as I know, in many of such trials and experimental campaigns, they did indeed observe formation of different amino acids and also simple peptides. So yeah, I think that robotics can speed up this whole process, and if we can quantize, like get exact amounts of every single product, so the yields, we can maybe possibly further, like in the future, can be sure how, let's say, RNA could have formed from abiotic compounds.
Thank you so much.
Okay, thank you very much. So as what Galimjan has said, so it's all about the characterization technique during the robotics process. So in his example, it's more on the UV and so on. So for proteins, you have just to more like in chemoreceptors in order for you to have a high throughput experiments. So any other more questions? Yes.
One of the pages, you presented some scope with their percentage yield. Did you obtain those values by the virtual computational means or by real lab experiments?
So you mean the distribution of yields across multiple dimensions, or is it like for specific reaction?
I think you presented some scopes. I think yes, maybe page 86, 40 if you can.
Sure. Yep. Or we can open this. Page 56.
Yeah, I think he's actually looking at the yields. So did you? It's experimental bits, so it's high throughput. So
I guess you were talking about these ones.
it's gone.
This one, or maybe this one.
No, a bit more. Can you go
Further.
back? Yeah.
Further. Okay.
I think before that.
Yeah, before this.
Right before this.
More.
This one's
More.
Page 6 should be.
Yeah, it's more that. Probably that one. I think this one.
Yes.
Oh,
Yes.
Yeah, so here in this project, our colleagues, they only used algorithms in theory, and they filter out all of the possible like new multi-component reactions. But when it was executed in the lab, they didn't use robotics here. So just wanted to say like the share like the history of this project. So the kitchen of this project is actually, this project took a very long time, and until it was published, the project was going on for like 7 years, and they were not able to use our robotized system before submitting it to the journal. but I guess that we can use hand in hand all of these algorithms in robotics to speed up the process. So yeah, maybe in the future we might see another
So these values were
application.
obtained by the virtual system. These values were obtained by the computer system. Then
No,
algorithm.
experimental.
So you mean the
By
yields?
experimental.
Yields are all experimental. So yields were all of these products, they were isolated, and then yields were quantified like using either mass, or if it's hard to isolate, then using NMR and internet standards. So anyway.
Okay, any more questions? So let's have one more question. Yes.
Thank you for your presentation. I would like to ask about the key calculations that you presented in your
Yes.
slide. So, what was the purpose of introducing that method? And do you integrate it or just kind of validate these results with your robotics algorithms?
Just give me a second. So it was during the discussion of this unknown pink compound, right? So yes,
This one.
as I said, we wanted to find the origin, the formation of this compound, and also its structure. And we only had the difference in spectrum. So for this reaction mixture, we got everything more or less correlated with known components, but for a known component, we get this picture. And we compared all of the spectra relevant to this reaction and this set of substrates already published in journals. And the data was not enough. That's why we decided to simulate the UV spectra ourselves. Yeah, and then find the nature of it.
Which software was used?
For DFT, we used Gaussian.
Gaussian.
Yeah, and we did time domain DFT for this with dispersion correction and with multiple initial conformers that were inputted into the calculation.
So this all of the results are from DFT calculations.
Yeah, so on this slide, all of the spectra are simulated from DFT.
Okay, thank you so much. So that's it for this afternoon. So we would like to thank Galimjan for the very, very Okay, so Galimjan, any parting words before?
Yeah, I just wanted to say once again, thank you very much for coming here and supporting me during this presentation. Thank you very much.
Okay, thank you very much to everybody. Okay, before we go, probably we'll have a picture with Galimjan.
Shall we take a picture? In this corner, yes.
Yes, in the class. Yeah.